Welcome to EC Concept once again. So we are in the series of RCC short notes. Today we are going to look about the beam design. Okay. In the beam design, as per your examination perspective, that is state government or GATE or EAC. So I'm going to give the important points under the design of beam. The first one is there are 7 to 8 points we are having. So we will see one by one. First one is effective span. Okay. What is the effective span? Effective span means it is the span of beam that effectively participate in bending. So this word is important. Effective span means which is effectively participate in bending. Okay. So generally the center to center distance between the support we are considering as a effective span. Okay. Now this effective span for different beams. The first one is for a simply supported beam or a slab. For a simply supported beam or slab, L effective which is taken by IS 456 LC plus D. LC means this is the beam and this is the support. In between the support, the length is clear span. Okay, here LC is a clear span. Okay, B1 and B2 are the B1 width of support. B1 and B2 are the width of support and B2 are the width of support, and this is the effective depth. Okay, or this B1 divided by 2 plus LC plus B2 divided by 2, meaning the center of the support to the center of the support. Okay, this is the L effective calculation for simply supported beam or slab. At the same time, the continuous beam or slab. The continuous beam, there are two cases. That case is depends upon this condition, less than LC divided by 12, meaning if support width is less than LC divided by 12, okay, then L effective is same as the above case. L effective is same as the above case, meaning that's a simply supported beam. Okay, B1 and B2 is less than LC by 2, LC by 12, then L effective is equal to minimum of the same thing will come, LC plus D or B1 divided by 2 plus LC plus B2 by 2. Okay. Now, suppose if the support width is greater than LC divided by 12 or 600 mm, whichever is less, then L effective is calculated as follows. A minimum of, here L effective is equal to minimum of LC plus D by 2 and LC plus B by 2. Okay, meaning here we are considering the center to center distance. Suppose this is the span 1. For example, for span 1, this is the distance. Okay, LC plus B divided by 2. That is the L effective. Okay, and the similar manner for this span also they have taken us by considering these two supports are same width and they are taking L effective is equal to LC plus B by any one of the support width. Okay. Okay. Now, third case, if the beam is supported by a roller or rocket bearing, so this is the rocket bearing, then the L effective is equal to calculator the distance between the center of the bearing. This is the center of the bearing, this is the center of the bearing. Consider the distance between these two is the L effective. Okay. Next one is C, cantilever beam or slab. For a cantilever beam, LC is equal, this is the LC and L effective is equal to LC plus D by 2. At the same time, for rigid frame, the center to center distance between the support is the L effect. Okay. Now, first one is over. Now we are going to see the second one. That is the longitudinal reinforcement. Okay. What is the longitudinal reinforcement? There are two longitudinal reinforcement on a beam. Okay. We know that there is a beam. This is the beam. Here. There was a reinforcement. It's a tension reinforcement. And this is the compression reinforcement. And this is the stirrups. Okay. Stirrups. Now, this is the tension reinforcement AST, and this is the compression reinforcement ASC. This is the stirrups, that is ASV. Okay. Now see, first, what is the limited tension reinforcement and limited? What is the minimum tension reinforcement? Maximum tension reinforcement. Similar manner, minimum compression reinforcement, maximum compression reinforcement. The minimum tension reinforcement as per IS 456-2000 says AST minimum divided by B into D that shall be greater than 0.87 Fi. Why we are using the minimum reinforcement? For the condition of ductility and to prevent any sudden failure of a beam. Second one is AST max. AST max is 0.04 B into D. This is the total cross-sectional area of beam. This is the total gross total or gross cross-sectional area. Meaning, if you see the section, this is the section. Okay. In that, there was a reinforcement. Then from this top to the center of the reinforcement, we are taking small d. From top to bottom, we are taking the d. This is b. So this b into d means not b into small d, not b into effective depth. This is b into capital D. That means the overall depth. Okay. So 0.04 BD. Okay. In other way, you can say this is the 4%. How much this? This is the 4% of gross cross-sectional area. Next one is a compression reinforcement ASC. ASC minimum is equal no value. There is no value for minimum, but at least 2 bars must be provided. Be careful. At least, this is the question. At least 2 bars must be provided in compression zone for the purpose of ductility criteria. For what purpose? The ductility criteria. This also same. Minimum reinforcement is used for ductility criteria. Now, what is the ASC maximum? ASC maximum is similar AST maximum 0.04 BD. Why we are using this? For problems in compaction. So if you are increasing the area of the steel without any limiter, then automatically there is a problem for penetration of the concrete. Okay, so that's the reason you have to curtail or limit the maximum reinforcement 0.04 BD. So we can say this is also a 4% of cross-section area. Okay. Now third one is side face reinforcement. You know, when the depth of beam is greater than 750 mm, then 0.1% of gross web area, be careful, gross web area of AST, gross web area of gross web area of AST, which was provided on a beam equally distributed on both sides, and the spacing of two reinforcements should not greater than 300 mm. This is the thing. Now see, if the depth of beam is more than 750, then 0.1% of gross web area is provided as a side reinforcement, equally distributed on both the faces, both side, okay, with a spacing not more than 300 mm. Why we are using this side reinforcement? It is provided to prevent shrinkage of concrete along the longitudinal direction. That means the shrinkage which is happening, shrinkage in this direction, longitudinal direction. To prevent the shrinkage of concrete along the longitudinal direction, meaning if there is a shrinkage which was happening in the longitudinal direction, then there was a crack which is developed in the vertical direction. Because of shrinkage in longitudinal direction, then there was a cracks in the vertical direction. So these are the cracks. And to take care of any torsional effect, and this also used to take care of any torsional effect, the side reinforcement. Okay, so this is also important. And longitudinal direction. Now next one is nominal cover. So nominal cover means, so let me explain this. There is a beam section. In that beam section, this is the reinforcement. From this top to the center of the reinforcement, this is called as effective depth. From center of the reinforcement to the extreme is effective cover. From extreme to extreme is the clear cover. Okay, this I have drawn. Okay, then minimum nominal cover is governed by following criteria. 1. Type of structural member. Exposure condition means mild, severe, or so on and so forth. Then the fire resistance in terms of hours. So based on these three conditions, the nominal covers have been used. So IS 456 2000 says for slab 20, beam 20, column 40, footing 50. At the same time, SP 36, slab 20, beam 25, column 40, footing is 50. Understood? Now, the fourth one is the spacing of the reinforcement. First one is a minimum horizontal clear spacing, meaning, so this is a reinforcement in a cross section, minimum horizontal spacing. This is one bar, this is another bar, this is another bar. Then the bar goes perpendicular to this screen. Okay, think about it. This is the horizontal spacing. Okay, so minimum horizontal spacing, first one, maximum of the following. Diameter of bar, if equal diameter of bars are used. If these three bars are equal diameter, then you have to consider diameter of the bar. Now, diameter of large bar if unequal bars are used. If unequal bars are used, then consider the large diameter bar. The nominal size of coarse aggregate plus 5 mm. Then you have to use nominal size of coarse aggregate plus 5 mm. Then maximum horizontal center to center spacing. This is minimum and maximum. Okay. For FE 250 300, 415 180, then 500 is 150. Okay. Now I can write this. Horizontal spacing of reinforcement. Next one, the lateral stability of beam. The beam is laterally supported at the ends only. That means at the ends the beam is laterally supported. Then L unsupported is should not greater than minimum of 60 into B, 250 B into D square, B square divided by D. Similarly, for a cantilever, for unsupported should not greater than minimum 225 B divided by 100 B square divided by. Then note here for column, in the similar manner we will use for column also. For column, L unsupported should not greater than 60 B for laterally supported at its ends. And this is should not greater than 100 B square divided by B, 100 B square divided by D for laterally not supported at its end. Laterally not supported at its end. So this also you have to keep in your mind. And the next one is sixth one, arrangement of loading for maximum bending moment. So this is somewhat interesting. Okay, arrangement of loading for maximum bending moment. There are two types of bending moment. One is a sagging, another one is hogging. The sagging on the for getting sagging span moment, sagging support moment. Similarly, for hogging span moment, support moment. So we are going to see one by one. First of all, we have to see for getting maximum sagging span moment. Second one is for getting maximum sagging moment at the support. So let us take a beam, continuous beam over that. Now in order to get a sagging maximum span moment, what you have to do, keep the load under the consideration. Keep the UD under the span which is considering, and then keep the load to the alternate span. Okay, suppose if you want a maximum sagging moment at this span, then keep the load on this span, and you have to keep the load alternate span. Okay, the loading shall be placed on under consideration plus alternate span. Next one is for getting maximum sagging moment at the support. Maximum sagging moment at the support, if you want, then what you have to do, you have to place the load. Okay, place the load, the span which is next to the adjacent span of this support. For this support, these two are the adjacent span, but you have to keep next to the adjacent span and alternate span. Okay, next for maximum hogging span moment, suppose if you want a maximum hogging span moment at this point, you don't apply the load at this point and keep the load on the alternate span. Okay, suppose maximum hogging moment at the support if you want, then keep the load adjacent to the span of the support and alternate span. Okay, so these four data are very very important. Keep in mind. Seventh one, this is the effect of shrinkage. See, there is a concept. You know, there is a beam. Generally, we will use a tension reinforcement at the bottom. So, because of the tension reinforcement, the temperature stress will be less in the bottom, more in the concrete, meaning the shrinkage stress. Okay, the shrinkage is the effect of temperature. The shrinkage stress will be more at the top and less at the bottom. Why? Because here the steel is there, here the steel is not there. Okay, because of this, unequal stresses is developed, so that there was a bending will be happen, because here the stress is less, bottom stress is more, so something like that bending is happen. Okay, how to avoid? You have to avoid by keeping the equal amount of reinforcement at the top also then the shrinkage will be uniform at both top and bottom. Therefore, we can able to avoid this. Okay. Now see effect of shrinkage. Due to presence of bottom steel, bottom fiber shrinks less. Bottom fiber shrinks less as compared to the top fiber. This differential shrinkage produces curvature which results in the deflection of the beam. This differential shrinkage, here one type of shrinkage, here another value of shrinkage. So this difference value will produce a curvature that is responsible for the deflection. By providing equal percentage of top and bottom reinforcement, shrinkage deflection can be eliminated. As I said, how can we eliminate it? By providing equal percentage of reinforcement at the top and bottom, the shrinkage will be eliminated. Understood? That's the thing. Now next one is total deflection calculation. This is a very important examination question. Total deflection. That deflection total is the summation of deflection due to load, deflection due to shrinkage, deflection due to creep. Okay, so delta T deflection due to load plus deflection due to shrinkage plus deflection due to creep. Out of these three, deflection due to shrinkage and creep is long term effect. Because of the long term effect or long term, the shrinkage and the creep effect will be more. So the deflection also more. Because this is a long term effect, you have to consider Young's modulus of concrete for long term. This is suddenly happened, that is short term. So this is a short term condition, therefore you have to use Young's modulus of concrete. Okay. Now total is equal to, this is a load, so therefore short term Young's modulus is used. This is the short term effect, this is the long term effect, these two. The long term modulus of elasticity is used for this case to calculate deflection. Generally, we know that the deflection is directly proportional to 1 by EA. Now, if you are going to calculate the load effect, then this is Young's modulus concrete. If you are considering shrinkage and creep, then you have to consider EC theta into I. Then if you submit these two, you will get a total deflection. Okay. The next one is a deflection limit that we are going to see. It is very important under this total deflection. The final deflection due to all loads, including effect of temperature, creep, shrinkage, measured from cast level of support. Measured from cast level of support should not exceeded by 250. L effective divided by 250. This is the first statement. Very important examination question. Second one is the final deflection including effect of temperature, creep and shrinkage after erection of the partition. Be careful, after erection of partition load and application of floor finishes should not be exceeded by L effective by 350 or 20 mm, whichever is lesser. Okay. Now third one is IS 456-2000 gave a deflection control. Why deflection control? Because calculating the deflection exactly, it is very difficult. You need more mathematical calculation. So that in order to avoid such kind of mathematical things, IS 456-2000 gave directly the values. The exact calculation of deflection and keeping it within the permissible limits needs a lot of calculation. IS 456-2000 provides a simplified approach to keep deflection of beam within the permissible limit. That limit is defined by L effective by effective depth ratio. Satisfying following condition, then the beam is safe in deflection. This is the important data. cantilever beam, that L effective by D is 7. For simply supported beam 20. For continuous beam 26. Now this is the deflection ratio L effective by D, which is less than, shall be less than K1, K2, K3, K4 and values. Here values means what? Cantilever means 7, simply supported means 20, continuous means 26. That is the meaning. The K1, the first one is a K1. K1 depends upon factor of span. The K1 is equal to value is 1 if the span is up to 10 meter. Suppose if the span is beyond 10 meter, okay, then you have to use in the place of K1 is 10 divided by span. And this is only applicable for simply supported beam and continuous beam. Okay, not for cantilever beam. Then K2. K2 is depends upon percentage of tension steel. Very, very important. For a given bending moment, if the percentage of tension reinforcement is increases, the section size decreases. See, the simple thing is, if the percentage of tension reinforcement is increases, then the depth of the beam is decreases. It means the deflection will be more at a higher percentage of steel. The deflection will be more. If the depth is decreases, then the deflection will be more at a higher percentage of steel. So we can write that deflection is directly proportional to percentage of tension steel. This is simple meaning. Okay. So see, let me explain this. L effective divided by D, which is equal to, this is less than K1, K2, K3, K4 into values. Now, what is L effect in this D? K1, K2, K3, K4 into values. Okay, which is D. Now, if the percentage of tension reinforcement is increases, then the section sizes decreases. This section sizes decreases. The D value will be decreases. Meaning what? K2 is increases. If the K2 is increases, then D is decreases. So D is decreases, meaning the deflection will be more. If D is decreases, the meaning is the deflection will be more at a higher percentage of steel. Next one is K3. K3 depends upon compression steel. Here, as percentage of compression steel is increased, K3 increases. Meaning L effective divided by K1, K2, K3, K4 less than D. So here K3 is increases as the percentage of compression steel is increases. So that K3 is increases, because the K3 is increases, the depth will be reduced, right? It means the depth requirement to satisfy the deflection criteria is less. The depth will be reduces at a higher percentage of compression steel. In other words, if the compression steel is reduces the deflection of the beam. Okay, in short, I can write here percentage of PC increases, then K3 increases. If K3 is increases, then D is decreases. If the D is decreases means what? Y is decreases. D is decreases, Y is automatically reduces. Then K4 is depends upon the ratio of web width to flange width of the beam. Okay. Here note, the value K decreases as we move from rectangular section to flange section. Be careful. the net value K, which is reduces from rectangular section to flange section, meaning the rectangular section having lesser deflection than the flange section. Okay, it means higher depth required for flange section to satisfy the deflection criteria as compared to rectangular section. Okay, so in other words, flange section produces more deflection than rectangular section. Be careful. If you need more depth, then deflection will be less. If your depth is less, okay, sorry to say, sorry, that is mistake. That is, if the depth is less, then the deflection also less. If the depth is more, the deflection also more. Okay, if the depth is less, then K is maximum. K is maximum, then that conditions, okay, that is percentage of reinforcement or a section, okay, those things will be changed. For example, rectangular section having less deflection, okay, but the flange section having more deflection. So that is the meaning. So you have to keep in your mind this. Understood? So I hope you understood. You have to read this at least 3 to 4 times so that you will get some idea. Okay, so thank you.